All right, alpha beta unsaturated carbonyl compounds. Recall using the common naming system, if you have a carbonyl carbon, the carbon next to it is the alpha carbon, and the carbon next to that would be the beta carbon. And so we call these alpha beta unsaturated carbonyl compounds because it's just so obvious. There's a double bond, which means unsaturation between the alpha and the beta carbon, and it's a carbonyl. Alpha beta unsaturated carbonyl carbon. We know this unsaturation starts alpha to the carbonyl right next to the carbonyl. But note, double bond, single bond, double bond, this is a conjugated system, which means we can have resonance forms here. The double bond can come over, or this double bond can break, or the pi bond break, put the electrons up here, giving a partial positive charge to this carbon. From this resonance form, the pi bond here can break and form a pi bond here, giving positive charge to this carbon over here. So the long story short is, when you have alpha beta unsaturated carbonyl compounds, not only is the carbonyl carbon partial positive, the beta carbon also has partial positive charge due to this resonance. We have partial positive charge on the carbonyl carbon. We have partial positive charge on the beta carbon. So if you are a nucleophile, you could add to the carbonyl carbon 1, 2, or you could add to the beta carbon 1, 2, 3, 4. It's as if we've heard these 1, 2, and 1, 4 questions before. But yeah, that's what can happen. Because recall, with resonance forms, this is the beast that is floating around in solution. This is what's in solution here. So any negatively charged thing floating around, such as a carbanion, will see positive charge here and positive charge here. And the question is, which one will it go to? I really, really hope that the stuff we learned a couple chapters ago with 1,3-dienes comes into play here. Let's take a look. Okay, let's look at the mechanism here. Here is our alpha beta unsaturated carbonyl compound. We're going to start with 1,2 addition. We have our strong nucleophile here, attacks the carbonyl, breaks the pi bond, which becomes a negative charge here. Yeah, this is ketone, no problem there. And so we have aqueous workup, and we form the alcohol. So our nucleophile goes on the carbonyl compound, or goes on the carbonyl carbon. The oxygen of the carbonyl becomes an alcohol. We keep the double bond where it is. When 1,2 attack occurs, this is 1,2 addition, and the nucleophile attacks carbonyl carbon, the double bond of the alpha beta unsaturated carbonyl compound stays put, does not change. Let's look at the 1,4 process, though. If the nucleophile attacks the beta carbon, because it has partial positive charge, then the pi bond will break and form a lone pair on this carbon here, the alpha carbon, making it a carbanion. Now, that will have resonance. We can just put the pi bond here, but then this pi bond will have to break and put the lone pair up on the oxygen, so that's what will happen. This lone pair on this carbanion becomes a pi bond between these two, and the pi bond here breaks, becomes a single bond. The pi electrons become non-bonding lone pair electrons up here, and we have the negative charge up here. Now, here's the fun part. This is what we call the enolate anion. This beast here, enolate anion, just like before up here, enolate anion will accept a hydrogen from the aqueous workup, a proton here, to become this beast. And we have seen this beast before. Anytime you have a carbon-carbon double bond and one of the carbons containing the double bond also contains an OH, that's an enol. Remember, enol. And let's be specific, the one carbon of the double bond also contains the OH. This is the enol. We call this the enolate anion because it's an enol without the hydrogen. We've taken that hydrogen off to make the anion, so it's the enolate anion. But wait a minute, we've seen enols before. Enols undergo keto-enol tautomerization. Recall that enols are unstable, and we are going to quickly tautomerize. quickly, hopefully, maybe not so quickly, we'll learn about that later on, where the double bond is going to end up here, and this hydrogen is going to end up on this carbon. Recall that tautomerization. The OH becomes a carbon double bond oxygen, and this H ends up on the carbon alpha to the carbonyl to make the ketone, which is more stable. But let's look at this. Here we have this situation, this enolate anion, but it has resonance forms, right? What if instead of the oxygen attacking the hydrogen to protonate, what if this carbanion attacks the hydrogen? Because when we're looking at the resonance hybrid, we're going to have negative charge on this oxygen and negative charge on this carbon. So two negative charges possible to attack that hydrogen. This first way we looked at it is if the oxygen attacks a hydrogen, forms the enol, and we get the keto form through tautomerization. What if the carbanion here, through resonance, attacks this hydrogen? Well, then that hydrogen just goes straight there, and we arrive at the same ketone. So that's pretty sweet. It doesn't matter which resonance form you pick to do the reaction, you end up at the same ketone after 1,4 addition. Okay. Note, let us review. After 1,4 addition, the double bond to the oxygen remains. The double bond between the two carbons is gone, and the nucleophile is on the beta carbon. 1,2 addition, the double bond between alpha and beta stays. The carbonyl is gone, and we've got an oxygen on that a hydrogen on that carbonyl oxygen, and a nucleophile on the 1,2 carbon. So the nucleophile with 1,2 goes on the carbonyl carbon, double bond stays. 1,4 addition, nucleophile goes on the beta carbon, double bond is gone, carbonyl stays. All right. So, wouldn't it be nice if we could just memorize what reagents are going to add 1,2 and what reagents are going to add 1,4? Good news for you, we can. It turns out organolithium and Grignards are more reactive of our two organometallic reagents. When they react with alpha-beta unsaturated carbonyl compounds, always go via the 1,2 addition. So they're going to attack the carbonyl compound. They will form the alcohol, and the carbon-carbon double bond stays. Organocuprates, on the other hand, with alpha-beta unsaturated carbonyl compounds, go via 1,4 addition. Organocuprates, the carbanion will attack 1,4. The double bond is gone, but the carbonyl stays, which means if we have this molecule here, note, carbonyl, double bond starting alpha to the carbonyl. This is our alpha-beta unsaturated carbonyl compound. Take our organometallic reagent. There's a lithium here, so this is organolithium. We know this is going to attack 1,2, so we know this group here, carbon, triple bond, carbon, hydrogen, is going to be on the carbonyl compound. This will become an OH, and the double bond stays. Yep, that's what we get. If instead we take the same starting material and react with this dimethyl copper lithium compound, followed by water, we know, okay, this is organocuprate. It's going to attack 1,4, which means a methyl group is going to go on the beta carbon. Right here, we're going to get a methyl group on the beta carbon. The double bond will be gone, but this carbonyl will still remain. Yep, carbonyl still remains. Double bond gone, methyl group on the beta carbon. So memorize that. Organolithiums and Grignards, 1,2. Organocuprates, 1,4. When dealing with alpha-beta saturated uncarbonyl compounds. Alpha-beta unsaturated carbonyl compounds. Good news. We're at the last part of this chapter. Let's take a look at synthesis here. Because we've found ways to make carbon-carbon bonds. We know a lot of stuff here. So starting with this alcohol and this alcohol, how can you make this compound here? Well, if you look at it, hopefully we can see, okay, I'm seeing this right here, this CH3, CH2, CH3. That's right here. We've got an OH there, but there's a carbon here. But look, I've got two methyls. This is kind of like an isopropyl group here with a CH2 on it. That would make this an isobutyl group. And here, well, I've got CH3, 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 CH3. I've got that, and I've got that extra carbon here. So no, count your carbons. Look where the carbon is. Want this carbon, this one, this one, this one. 1, 2, 3, 4 carbons here have to be 1, 2, 3, 4. Those four carbons there. These 3 carbons here of this isopropyl part are right there, which means this carbon, that's the carbonyl carbon, has to be this one right here, because that's our only carbon left. You know, this carbon here has to become the carbonyl carbon. All right, so how are we going to work this? Well, if this is going to become the carbonyl carbon, this carbon is going to have, we're going to have to form a bond between this one and this one. So what if we made this carbon over here a carbanion? Well, it's an alcohol. How do we make it a carbanion? Well, we could try a little substitution with HCl, protonate that. That's secondary. Oh, you're looking at a world of hurt. I would go with SOCl2. I'd put in thionyl chloride because we know thionyl chloride changes alcohols into chloros. So this OH goes away. We put a chloro on there. And once we have this chlorine on there, throw in some magnesium, and now we've got a Grignard reagent with this sec-butyl magnesium chloride here. Okay, I've had this molecule up here with the OH on it. I know if I add PCC, pyridinium chlorochromate, I can oxidize this to the aldehyde. Recall, PCC oxidizes primary alcohols to the aldehyde. It stops at the aldehyde. Well, now I've got an aldehyde, a carbonyl compound. I've got a magnesium, a Grignard reagent here, so I know that this carbon is essentially a carbanion. So I can form a bond between this carbanion and the carbonyl. Followed by water, I've got this bond here. So now I've just taken this group, it's now right here. My aldehyde carbonyl is right here, becomes the OH as we just learned. But wait, this is just a secondary alcohol. I know PCC, and truthfully, potassium dichromate, K2Cr2O7, will also work to oxidize a secondary alcohol to the ketone, and I have my final molecule here. So you need to start doing this, start working on synthesis and saying, okay, how do I make this? How do I make carbon-carbon bonds? Anytime you have a carbonyl, you know you can always reduce it to an alcohol. So maybe with an OH there, that will give you an idea of what to do. You know that you can make carbon-carbon bonds using organometallic reagents. And so if you can change one to an organometallic and one to a carbonyl, then we can make these bonds. Start thinking about those issues. Here's another synthetic problem. Starting with alcohols of 5 carbons or less, make this molecule right here. Note we often start with alcohols because alcohols are inexpensive. They're cheap to buy. They transport really well. There's no special handling of them, and they're relatively non-toxic. So they're stable, they transport well, they're cheap. Nice. So we usually start with alcohols, 5 carbons or less, because those are the cheaper ones. How do you make this molecule? Well, excuse me, we note that we're going to have to make carbon-carbon bonds somewhere because our final product has 5, 6, 7, 8 carbons. How do we do it? Well, here's a couple ways. One way is to start with this group here. Well, actually, let's look at the opposite way. Working backwards. Let's see. If I had an OH on here, right there, I know that I could have made a bond between this carbon and that carbon if this was a negative charge and this was a carbonyl. So if I had cyclopentanone and there was a carbonyl on this carbon, I know I could tack it with an alkylithium or a Grignard and form this bond, and that would make the OH. I also know if I have an OH, but I need to get to here, that I could get rid of that OH several ways. One nice way is just acid catalyzed dehydration of an alcohol to form this alkene, and note it'll form the more substituted alkene. Good old Markovnikov. Oh, remember Markovnikov's rule? Remember Zaitsev's rule? If you don't remember them, look them up. You need to know them. And then I know if I have a double bond, H2 platinum on carbon will get rid of that double bond. We'll add hydrogen across that double bond to make our alkane. So the question is then, how do I get a carbanion and how do I get this alcohol when how do I get this carbonyl compound, the cyclopentanone that I'm going to need? Well, I know if I have this 5-carbon alcohol and PCC, pyridyl chlorochromate, I can oxidize this alcohol, the secondary alcohol, to the ketone. So that's pretty straightforward. Secondary alcohol, the cyclopentanone, PCC, boom, you got your carbonyl that will get attacked. So then the question is, how do I make this be a negative charged carbanion? Well, I know if I started with this alcohol, add PBr3, that'll put the bromine on there, add magnesium or solid lithium, and you get our Grignard reagent, which will react with this, and boom, there we go. Yeah. Synthesis takes time. I'm sure at this point you're not quite seeing everything. Note synthesis is kind of nasty. You have to remember all of your organic 1 reactions so that you can apply them to do the organic 2 stuff. Note that we learned about this step, reduction, in organic 1. We learned about this step, acid catalyzed dehydration of an alcohol to form an alkene, in organic 1. We learned about this oxidation in organic 1. We learned about alcohols to alkyl halides in organic 1. Heck, the only reaction that we've learned from organic 2 was making the Grignard reagent and then reacting a Grignard with a ketone. So this little part right here was the organic 2 stuff, and all the rest was organic 1 stuff. So make sure you really know your organic 1 reactions. You'll need them to do synthesis. And synthesis takes time. I would fully expect that if I just gave you this problem, it would take you hours to figure this out at the beginning. But as you get more and more used to synthesis, you find that there's certain things that you're always doing, certain steps that you always do, such as hydrogenation, such as acid catalyzed dehydration, PBr3 to change alcohols into alkyl halides, oxidations, reductions. We're always doing them in our synthesis, and those are a lot of organic 1 type of issues. All right, so this ends this chapter. It was a bit of a beast. We will go on to the next chapter in our series. Let's take a closer look at nucleophilic acyl substitution.